Today I'd like to talk about trig substitutions. We're going to use three different types of substitutions depending on what sort of integrals that we have. If we have an integral that contains a factor that looks like radical constant squared minus u squared, where u is the variable, or radical a squared plus u squared, or radical u squared minus a squared, where a is presumed to be a positive constant and u is a variable, then we're going to make the substitutions u equal a sine theta, where theta is between negative pi over 2 and positive pi over 2. In this case, we'll look at u equal a tangent of theta, where theta is strictly between negative pi over 2 and pi over 2. And we'll look at this one with the substitution u equal a secant theta, where this gets a little tricky. Theta could be as small as 0 and less than pi over 2, or theta could be bigger than pi over 2 and less than or equal to pi. The reason that we have to use this piecewise definition is that the secant function is not continuous on the interval from 0 to pi. It has a vertical asymptote at pi over 2. I want to think about square root a squared minus u squared. We're going to let u equal sine of theta, where theta is in this range of values. This is important because it's on that range of values that we can undo the sine function with the arcsine function. The square root of a squared minus u squared, if you write in that u is a sine theta, can be written this way. One of our trig identities says that 1 minus sine squared theta is cosine squared theta. Now, we're presuming the a to be positive, so radical a squared is just a, but you have to be very careful about something here. Generally speaking, radical z squared is not z. That only happens if the z is positive or 0. So strictly speaking, I should write a times absolute value cosine theta. Our choice of which thetas that we're looking at is going to allow us to get rid of those absolute value signs, though. If you think about the unit circle way of dealing with trig functions, the angles negative pi over 2 to positive pi over 2 is the right hand, that is, part of the circle. The cosine is the x coordinate on the unit circle. Cosine of theta is at least 0, so that means absolute value cosine theta is just cosine theta. And for this choice of theta values, which is turning out to be useful for us, radical a squared minus u squared is just going to be a times cosine theta. Radical a squared plus u squared is going to be dealt with in a similar way. We're going to set u equal to a times tangent of theta. This time, though, theta has to be strictly between negative pi over 2 and pi over 2, because tangent of theta is undefined at the end point. Looking at what radical a squared plus u squared will be, there is a trig identity that says 1 plus tangent squared is secant squared. I can break this up into two square roots to look at. We presume that the a is positive. You might think, what if it's not? Well, a shows up only as a squared, and negative of 7, when you square it, is the same as you square 7, so it doesn't make any difference. We do need to worry about radical secant squared theta, though, but on the other hand, we're still either in the first or fourth quadrant in terms of the angle. The cosine is positive there. 1 over the cosine, which is the secant, will be positive. Absolute value of a positive number is just the number, so we can lose the absolute value signs again. The last one is trickier. If you look at the square root of u squared minus a squared, if u were positive but smaller than a, the quantity underneath the square root sign would be negative and you'd be unable to do the calculation. If u were further to the right of negative a, but not as far as a itself, you would still get a negative number under the radical. So cosine of theta, when theta is between 0 and pi over 2, is less than 1. That means that secant of theta will be bigger than 1. And if u is a times secant of theta, u is a times a positive number that's bigger than 1. This part goes with u being at least a. On the other hand, if the angle is between pi over 2 and pi, cosine of that angle is negative, secant of that angle is negative, a times secant would be a negative number. It's this range of angles that go with u being negative and less than or equal to negative a. In any case, when you calculate this radical symbol, it is not negative. We talked about that when we were talking about inverse functions. So when I do the usual simplifications here, the secant squared of theta minus 1 is tangent squared of theta. I don't feel bad about breaking this up into two square roots. We're assuming that the a is positive. Radical a squared is a, and radical of the square of tangent theta is the absolute value of tangent theta. And now we have an actual problem. If you're in this first part where the u is bigger than or equal to a, then tangent of theta is positive. But if in this part, tangent of theta is negative. So if u is bigger than or equal to a, I can just lose these absolute value signs because that corresponds to theta being between 0 and pi over 2. And if it's the other way, I'm missing a negative sign. So putting all these pieces together, radical u squared minus a squared, when we let u equal a secant of theta, is going to be a times tangent of theta if theta is between 0 and pi over 2, and it's going to be negative a times tangent theta otherwise. Tangent of theta will be negative. Negative times positive is negative, and put the negative sign on, which turns this into a positive number, which radical of anything has to be. That is to say, square root of u squared minus a squared using our substitution is going to be a tangent of theta when u is bigger than or equal to a, and negative a tangent theta if u is less than or equal to negative a. So what does this have to do with anything? Let's look at the integral of x cubed over radical 1 minus x squared integrated with respect to x. The first thing I think of when I look at that is I think to myself, it's too bad it's not an x squared up here, because then I could just do a u substitution. Unfortunately, it's x cubed. And also, I'd like to mention at this point, on the last test, there were a large number of people who seemed to think that the dx was not worth writing down. You have to take care of the dx. If you don't, as we'll see in a minute, you're sunk. Instead, though, instead of thinking about having an x squared there, I'm looking at 1 minus x squared. That's 1 squared minus the square of x. So the a is going to be 1 and the u is going to be x. we're supposed to let the u equal a sine theta. U and x are the same thing here. So I'm going to let x equal a sine theta, where theta is between negative pi over 2 and positive pi over 2. And as I keep saying, that's important because at the end, it's going to let us undo this sine function with the arcsine function. This square root that we're talking about is square root 1 minus sine squared x, which is square root cosine squared x, which strictly speaking, we ought to write as absolute value cosine x, cosine theta that is. But because of the range of theta values, we know that that cosine isn't negative, so I can just drop the absolute value symbols and pretend that they weren't there. Don't forget to think about the dx though. X is sine theta, where theta is in the good range. Dx d theta is cosine theta. Dx is cosine theta d theta. So I'm going to write that here instead of writing dx. If I thought the d thing was not important, I'll be unable to cancel the cosine of thetas out in a minute, and I'll get the wrong answer. But being careful, we write the dx down, cancel cosine theta out. This is the integral sine cubed of theta with respect to theta. But in a previous discussion, if I have powers of cosine, 0 would be a power, times an odd positive whole number power of sine theta, we know what to do. You split off one of those sine thetas here, take the remaining things, sine squared of theta, and use a trig identity to write it as 1 minus cosine squared theta. We're going to let u equal cosine theta. The derivative of u with respect to x is negative of sine theta, negative 1 times sine theta. So du is negative 1 times sine theta d theta. Negative 1 times du is sine of theta d theta. And the reason that I wanted to express it in this way is right there, I have sine of theta d theta, which is negative 1 times du. The integral that we're looking at now, 1 minus cosine squared, 1 minus u squared. Negative 1 du is sine theta d theta, negative 1 du. So this is going to turn this just into a polynomial. To make life a little bit easier on myself, I'm going to use the associative law to group together the quantity 1 minus u squared multiplied by negative 1. The negative of 1 minus u squared is u squared minus 1, so there is no need to carry this extra negative sign around with it. So I have to do the integral of u squared minus 1 with respect to u. This would be 1/3 u cubed minus u plus the constant of integration. Of course, u is cosine of theta, so I can go ahead and write that in. But then I have a problem. I want my answer to be in terms of x, but it's got theta in it instead. So the way people usually deal with this kind of thing is to use the relationship between x and theta to actually figure out what cosine of theta is. X is supposed to be sine of theta. That is to say, sine of theta is supposed to be the number x. I can draw a right triangle that represents this situation. I'll have angle theta here. And you remember that sine of theta is opposite over hypotenuse. So I'm just going to label the opposite side to be something and the hypotenuse to be something else, so that when you figure opposite over hypotenuse, it comes up equal to what I want it to be. There's lots of ways you could do this, but the laziest thing I could think of was to say this is sine of theta and this is 1. Opposite sine theta over hypotenuse, 1 is sine theta. But once I know all three sides of the triangle, I'll be able to figure out any trig function of theta that I want. This side squared plus that side squared has to equal 1. So it follows that this side must be radical 1 minus sine squared theta, which, if we hadn't predicted it ahead of time, is equal to cosine theta. And cosine theta is radical 1 minus sine squared theta over 1. That would be square root of 1 minus x squared. So by drawing a little triangle, I can convince myself of what cosine of theta has to be. This is the preferred method for dealing with this sort of thing. As far as I'm concerned, what we had written on the previous page is a perfectly good way to represent the situation. However, you can try to factor some things out. If you factor out a 1 minus x squared to the 1/2 power, the part that remains inside, 1 minus x squared, is going to be raised to the 2/2 power, which is 1. So this is just going to be 1/3 times 1 minus x minus 1, x squared that is. That would be 1/3 minus 1/3 x squared minus 1. And then you can factor a negative 1/3 out of the result and have this as your antiderivative. As far as I'm concerned, though, the answer that we had on the bottom of the previous page is a perfectly good way to represent this. I want to look at a slightly more complicated situation in which the numerator isn't just a single term. I'd like to look at the integral of the fraction 2x cubed plus 1 upstairs and square root of 4 minus x squared downstairs. In view of what we did before, obviously I should let x equal to 2 times sine of theta, where theta is in my very nice interval of values. Square root of 4 minus x squared, when all the dust settles, is going to be 2 cosine theta. I have to take care of the dx, though. Dx d theta is 2 cosine theta. Dx is 2 cosine theta d theta. So upstairs in my fraction, I'm going to have 2 times x cubed, 2 times the cube of 2 sine theta. Then I'm going to add my 1. I divide by square root of 4 minus x squared, which worked out to be 2 cosine theta. And then the dx is 2 cosine theta d theta. If I had not seen to do the dx part, I wouldn't see that things are actually pretty nice. The 2 cosine thetas are going to cancel out. Having canceled them out, 2 cubed is 8, and I had that other factor of 2, so I'll have 16 times sine cubed of theta plus 1 integrated with respect to theta. Now I can break this up into the integral of 16 sine cubed with respect to theta plus the integral of 1 with respect to theta. In the first chunk, I can factor a 16 out and see that what we have to do is 16 times the integral of sine cubed theta d theta plus the integral of 1 d theta. And there's some extremely good news. The integral of sine cubed theta d theta is what we were just looking at a minute ago. We already know that integral. This integral, if theta is the variable and antiderivative is theta here, so I'm just going to write down the answer from my previous problem, multiply it by 16. plus integral of 1 d theta is theta plus a constant. We're almost done. We're done with the calculus, in fact. My only problem is that the answer that I've gotten is written in terms of both x and theta, and we want to have this in terms of x's alone because that was the original variable. This is not very difficult, though. X is 2 sine theta. That means x over 2 is sine theta. And remember, theta is in the angle negative 90 degrees to positive 90 degrees. This means it's safe to hit both sides of that equation with the arcsine function. Theta is the arcsine of x over 2. And finally, you can write your antiderivative down. Sometimes you'll have a situation in which it doesn't look like any of our ideas work, but with only a little bit of trickery, we can see that they do. I want to think about the integral of 1 over square root of 8 minus 2x minus x squared. And what I want to do to get started on this is I just want to think about the quantity that's underneath the square root sign. So I'm going to have 8 minus 2x minus x squared. You could write that as 8 minus the quantity x squared plus 2x. What I'm going to do is I'm going to complete the square and see if I can't make this look like something I can vaguely deal with. So I'm going to take x squared plus 2x, cut the 2 in half and square it, and say, I wish it said plus 1. So I'll make it say plus 1. Of course, I've got to correct for that by subtracting 1 away, or I'm not talking about the same quantity anymore. The reason that I'm wanting to do that is that x squared plus 2x plus 1 is a perfect square. So the quantity underneath the radical sign is 8 minus, in parentheses, the square of x plus 1 minus 1. So it's 8 minus the quantity x plus 1 squared, minus minus is plus 1. The quantity underneath the square root sign is 9 minus the square of something, but it's not the square of x, it's the square of x plus 1. If you think about this as square root of a squared minus u squared, the a squared would have to be 9, so a would be 3, and the u would have to be the thing whose square I'm subtracting away from that 9. The u would have to be x plus 1. And in our recipe, we said when I had square root of a squared minus u squared, the cookbook recipe that I'm going to do is u equal a sine theta. So u is x plus 1, a is 3 times sine of theta, where theta is in the nice range of values. I'm going to need to do something about the dx in this integral. Take both sides of this formula and differentiate it with respect to theta. 1 is a constant, so its derivative is 0, and the derivative of x with respect to theta is derivative of x with respect to theta. On the other hand, the derivative of 3 sine theta is 3 times cosine theta. So this tells me that the dx is going to be 3 cosine theta d theta. As usual, our square root works out to be a times cosine theta. So 1 over square root 9 minus x plus 1 squared, when all the trigonometry is done, is 3 times cosine theta. The dx is 3 times cosine theta d theta, and then a miracle happens. Almost everything disappears. I just have to have an antiderivative of 1 with respect to theta, and that would be theta plus a constant of integration. All that remains to finish this is to turn it back into an expression involving x only. This time I don't even need to draw my triangle. X plus 1 is 3 times sine theta, where theta is in the nice range. That says sine of that theta in the nice range is x plus 1 over 3, which makes it safe to say that theta is inverse sine of x plus 1 over 3. So my antiderivative is arcsine of x plus 1 over 3. And then you add a constant of integration. As a sanity check, let's make sure that this is right. And remember, the derivative of the arcsine function is 1 over radical 1 minus the squaring function. Of course, since it's not arcsine of x as such that I'm doing the derivative of, I'll have to use the chain rule. The derivative of the arcsine function is 1 over radical 1 minus the squaring function, evaluated at x plus 1 over 3, and then you have to multiply by the derivative of 1/3 of x plus 1. Derivative of x over 3 is 1/3. Derivative of 1 over 3 is 0 because it's a constant. In this square root, I'll go ahead and write the square of the top and the square of the bottom in the x plus 1 over 3. 1/3 is 1 over square root of 9. So I'm going to put these back together using the properties of square roots. Having done so, I'll do the distributive law. This is 9 times 1, which is 9, minus 9 times something over 9, which is just the something. The thing that I'm subtracting away from 9 is x squared plus 2x plus 1. So we have 9 minus 1, which is 8, minus x squared minus 2x, and that is correct. That is the thing that we were integrating. Another example, I'd like to look at the integral of the following fraction, x cubed plus 1 over 4 plus x squared with respect to x. This time I don't have something squared minus something else squared. I've got something squared plus something else squared. If I want to think of it this way, the thing that's on the bottom of the fraction is a squared plus u squared, where a squared is 4, so a is 2, and u is x. We're supposed to use the substitution x equal a times tangent of theta, 2 times tangent of theta, in the range of values that are nice for the tangent function. Dx d theta is 2 times secant squared of theta. Dx is 2 secant squared theta d theta. So upstairs, x cubed is going to be what you get when you take 2 times tangent theta and cube it. 2 cubed is 8, tangent cubed of theta, and then I had plus 1. On the bottom of the fraction, you're going to have 4 plus 4 times tangent squared. That's 4 times the quantity 1 plus tangent squared. That's 4 times secant squared. So on the bottom of my fraction, I have 4 times secant squared theta. The dx is 2 times secant squared of theta with respect to theta. And as I keep saying, that denominator is important, the part that goes with the differential, that is. It cancels out these 2 secant squared of thetas. I'm going to have a 2 here and a 4 there. That provides a factor of 1/2, which I'll pull out in front of the integral so that I don't have to mess with it anymore. I'll do the integral of 8 times tangent cubed plus the integral of 1 with with respect to theta. In that first integral, I can pull the 8 out front. So this is reduced down to being able to integrate tangent cubed of theta on the one hand, and the constant function 1 with respect to theta on the other hand. We've actually already done the integral of tangent cubed of variable with respect to variable, but quickly, in case you forgot, split a factor of tangent theta out, convert the tangent squared of theta into secant squared theta minus 1, multiply this stuff up, split it into two integrals. This one's on our list of things we know. This one I can do with a u substitution, letting u equal tangent of theta. So the du is secant squared theta d theta, and you end up with 1/2 tangent squared of theta minus minus, which is plus, natural log absolute value cosine theta. Now, the relationship between x and theta was that x was 2 times tangent theta. X over 2 must be tangent of theta. And since we only allow thetas that are in the safe range, that tells us that theta must be the arctan of x over 2. So writing down all of my little bits, finally, my antiderivative is 2 tangent squared of theta plus 2 natural log cosine theta plus 1/2 arctan x over 2 plus a constant. This 1/2 is that 1/2. The only remaining issue is I don't want to see cosine of theta, and I don't want to see tangent of theta either. I only want to see things in terms of x. Actually, we already know what tangent of theta is in terms of x. It is x over 2. We don't know the cosine of theta, so we'll use our triangle idea in order to get these quantities. Now, there's two ways you can express these answers, though. Most people feel that the triangle way is a better way of doing it because the formulas don't look so clunky. But if you really insisted, theta is arctan of x over 2, so you could write cosine of theta as cosine of arctan of x over 2, but that doesn't really look very good. It looks more complicated than it needs to. The other way is this. Take the relationship between x and theta. X is 2 times tangent theta, meaning the tangent of theta has to be x over 2. I'm going to draw a picture of a triangle with angle theta in it so that tangent of theta is x over 2. There's an unlimited supply of triangles that would do that for me, but I'm going to do the simplest thing that I can manage. I'm going to look at angle theta. I'm going to look at the opposite side over the adjacent side and rig my triangle so that that fraction comes up to be x over 2. The laziest thing I can think of is to put an x here and a 2 there. I could have put 2x here and 4 there, but I see no reason to drag unnecessary complications in. Once I know those two sides, the Pythagorean theorem tells me the hypotenuse is radical 4 plus x squared units long, the square root of that squared plus that squared. We now know all 3 sides of the triangle. We can calculate any trig function that we feel like calculating. Cosine of theta is adjacent side to theta divided by hypotenuse, 2 over square root 4 plus x squared. Tangent of theta, which we already know, but in case we didn't, is opposite over adjacent. That would be x over 2. And now I have my cosine and tangent functions in terms of x. So finally, writing in all the bits, my antiderivative is 1/2 times the square of x over 2 plus natural log absolute 2 over square root 4 plus x squared plus a constant, plus the 1/2 arctan x over 2, which I forgot to write down on this page. As another example, I'd like to look at the integral of x cubed over square root 4x squared minus 9 with respect to x. This one is sort of tricky. If you think of x as being 0, that square root doesn't even make any sense. In fact, if x is too close to 0, the square root isn't going to make any sense because 4x squared will be less than 9. So there's going to be some x's for which this makes sense and others for which it doesn't. If you remember how you solve inequalities, you find out where the number under the square root can go from being positive to negative. 4x squared minus 9 is continuous, so the only place that that can happen at is a place where 4x squared minus 9 is 0. It turns out that there's two places where the quantity underneath the square root can change sign. One of them is at x equals 3/2. The other is at x equals negative 3/2. If x is bigger than 3/2, the number underneath the square root quantity will be positive and everything's good. If x is further to the left than negative 3/2, the quantity underneath the radical is positive again and everything is good. Between negative 3/2 and positive 3/2, though, that doesn't even make any sense to take square root of 4x squared minus 9 for such a number. So this is going to be that case where it splits up into two chunks. So for this problem to even make sense, I have to be a bit off to the left or a bit off to the right of x equals 0. I'm going to be intensely lazy and look only at the case where x is positive. If you look at 4x squared minus 9, that's what you get when you square 2x and then you square 3 and subtract them. So the u is going to be 2x and the a is going to be 3. I want u equal to a secant of theta. That is to say, I want 2x to equal 3 times secant of theta. And we're looking at the case where the x is positive. So we're only looking at angles that are between 0 and pi over 2. These would be the place where x was negative. So x is going to be 3/2 secant of theta. The derivative of that would be 3/2 secant theta tangent theta. So dx is going to be 3/2 secant theta tangent theta d theta. So when I write my dx down, instead of literally writing dx, I'm going to write that instead. Upstairs in my integral, I need to have x cubed. So if x is 3/2 secant theta, then x cubed is going to be the cube of 3/2 secant theta. Meanwhile, down on the bottom of the fraction, underneath the square root sign, I'm supposed to have 4 times x squared minus 9. So I'll have 4 times the square of 3/2 secant theta minus 9. This is much more complicated than what we've looked at before because of the secant tangent bit. There are some factors that I can pull out of this thing. I've got a factor of 3/2, so I'll pull it out in front. I'm also going to have a factor of 3 cubed over 2 cubed, 27 over 8. So I'll bring that out front as well so that I don't have to keep messing with it. I'm just going to leave it like this for the moment in case something else cancels out later. So a number, a constant, 27/8 times 3/2 times the integral of secant cubed over, underneath the radical sign here, I've got 9 multiplied by secant squared of theta minus 9. That's 9 multiplied by the quantity secant squared minus 1. That's 9 times tangent squared of theta. And since I know tangent of theta is positive, square root of 9 tangent squared of theta is 3 times tangent theta. And the dx, of course, as we said, is secant theta tangent theta d theta. There is some good news. I'm going to be able to pull a 1/3 out, but better than that, I've got a tangent in the denominator and a tangent in the numerator. Those cancel each other out, and I'll have just 3 factors of secant from that, 1 factor of secant from that. After I cancel the tangent of thetas and pull the 1/3 out front, all I've got left to do is to integrate secant to the 4th power of theta. So after multiplying the constants out front together, I'll have 27/16 times the integral of secant to the 4th power theta d theta, and we're glad to see that. I only have a power on a secant, and that power is a positive even number. We know what to do. Split off 2 factors of secant. This is one of our rules from the trig integral bit. Take the rest of it and say that secant squared of theta is the same as 1 plus tangent squared of theta. Now, if you were to multiply this out, you'd get secant squared times 1, which is secant squared. You'd get secant squared times tangent squared. So you can split this up into 2 intervals. The integral of secant squared of theta with respect to theta, plus the integral of tangent squared theta, secant squared theta, d theta. There's 2 things to know looking at this. One of them is we're very happy to see this part. Secant squared of theta is on our list of things that we know how to do derivatives of. The second part, until recently we didn't know this, but we're really happy to see this too. This is the integral of a power of tangent theta, secant squared theta d theta. It's already set up for us. We'll make a u substitution on this one, where u is tangent theta, and it'll turn out that this is easy to integrate. So antiderivative of secant squared theta d theta is tangent theta, and to deal with the rest of this, integral tangent squared theta secant squared theta d theta can be done by letting u equal tangent theta. Du d theta is secant squared theta. Du is secant squared theta d theta. That turns this integral into integral u squared du, which is 1/3 u cubed. And of course, u cubed is tangent cubed of theta, so that's this piece. I guess strictly speaking, it would look nicer if I wrote my constant of integration there. It doesn't make any difference. The only remaining issue is to convert the tangent of theta back into things involving x. Our substitution was 2x equal 3 secant theta, which says that secant of theta is 2x over 3. Expressing that in a more familiar way, cosine theta is 3 over 2x. So I'll draw my right triangle picture again. I want adjacent over hypotenuse to be 3 over 2x. So I'll make the adjacent 3 and the hypotenuse 2x. That'll do it. This distance squared is hypotenuse squared minus adjacent squared. So that'll be 2x times 2x minus 9. Square root is the square root of 4x squared minus 9. We can now calculate the tangent of theta is radical 4x squared minus 9 divided by 3, and substitute this in for tangent of theta in the two places where it appears, and you have your antiderivative. So what we've seen in this section is that under certain circumstances, we can take integrals that we previously were unable to do, and by using one of these three substitutions, turn them into an integral involving sines and cosines and tangents and secants, and solve them using the techniques from the previous section. I think it's pretty clear, though, that this can get fairly complicated, so a good amount of care is going to be needed when we do this sort of thing. Whatever you do, don't forget about the dx. Coming up next, partial fractions.